Yeah, Hardey-Weinberg equilibrium, it gives us information whether any kind of changes, genetic change is happening or no. Okay. As I
Mm-hmm.
told you before, Hardey-Weinberg equilibrium is applicable only and only in that population which has large size and it shows no mutation, no genetic changes. Correct?
Yeah.
And I told you there is Hardey-Weinberg formula, which actually it start with P plus Q is equal to what? 1. Yes?
Mhm.
Where P is the, what is P? P is a dominant allele
Dominant.
and Q is the recessive allele. If we are determining one trait which has a
Mhm.
dominant and recessive allele, so we can use this formula. The possibility, if we are talking about the possibilities, probability, we learned if P and Q are there, there will be possibility. This is 0.5 for this and
Mhm.
0.5 for this. So ultimately it will be the probability value will be the maximum, which is 1, correct?
Yeah.
Now, in order to figure out in one population, out of those two dominant and recessive allele, we cannot determine homozygous dominant or heterozygous number of frequencies for those alleles. But easiest way is to find out recessive allele number. It is easy to determine, and then this allele number we can use and we can figure out the amount of dominant alleles which are present and amount of heterozygous individual which are present for that particular trait in that particular population, correct? So
Okay.
now,
Yeah.
according to the Hardy and Weinberg, they proposed one equation which was p square plus 2pq, correct?
Mm-hmm.
And plus q square is equal to 1, isn't it? As
Yeah.
you already told, P square represent what? Homozygous dominant. Yes. Q square
Mm-hmm.
homozygous recessive. While PQ, they are representing heterozygous individual for that particular trait in that population. Now, for example, al albinism or albino people, this is recessive trait. Okay. And
Okay.
normal color, skin color is dominant trait. So if, for example, albinism or albino people we are focusing, so A will be represented for what? Dominant. Yes. And small a will be resembling recessive. Yes.
Yeah.
So for example, in one population of 20,000 individuals, 20,000 individual, one individual is albino. What
Mm-hmm.
is the percentage?
Of
One individual is albino.
yeah.
What you will do out of 20,000?
Yeah.
So I told you Hardy-Weinberg equilibrium can apply only to large number of populations.
Yeah.
Large number of population mean the chances of genetic variation, effect, it will not be that frequent, very
Mm-hmm.
drastic. They will change, but they will change very, very slowly. Okay.
Yeah.
Now please tell me what will be the number? 20,000, one out of
And then
20,000. It will be giving you what?
so wait, one person out of 20,000 is albino
20,000
or
is
1%?
albino. Yeah. So
Yeah.
what will be the q square? So obviously it will be q square. Yes.
Mm-hmm.
So 1 divided by 20,000. What is the answer? Tell me the answer.
1 divided by or
1 divided by.
0.0005.
No, 000. How many zeros are there?
4.
4 zeros. Yes. 4
Yeah.
zeros. So this is q square. Yes.
Mm-hmm.
If you want q values, what will be the value of q now?
You just would
Do
square
it, do
that.
it, do it. Yes. Tell me the answer.
I don't, 1 minute.
Do you have calculator with you or no?
Yeah.
I can do it on my own, but this the way I'm doing, you should know what exactly we are doing. Okay. You should
Mm-hmm.
go through your hand.
Yeah.
What will be this? 0 point?
0.007.
0.007. You got the value of Q 0.007. By using this and applying into this, can you find out the value of P?
Yeah. You
What will
subtract
be
that by
P first? What you will do now?
pardon?
What you will do? How you will find out the value of P now?
You can subtract the 0.007
From?
with 1.
Shabash, very, very good. Bravo. Okay. So if we are saying this will be P, so P will be equal to a dominant allele will be 1 minus Q, correct?
Yeah.
So it will be 1 minus 0.007. So value will come what?
0.993.
0.993.
993.
0.993. Correct? Now you
Yeah.
figure out if you put all these values into this one, you can easily find out. If I ask you, can you tell me the value of heterozygous individual in this population? Can you find out now?
Yeah.
Do it. And please do it on my screen.
Okay. 1 minute. How do I how do I do that?
No, you have a value of Q. You have value of P,
No,
correct?
no, no. How do I write it?
Or you cannot write on
Oh,
screen, or you can write now.
I can? Okay.
Yeah, it is there.
Okay.
Shall I remove my stuff so it become clear for you? Yes. You remember the
It's okay.
values? Yes. I remove my stuff.
Yeah. No, no, don't remove all of it because I don't
No,
remember.
I will not. I will not. I will remove only those things which are not required. Now you are finding out, look, you are finding out heterozygous, yes?
Mm-hmm.
Heterozygous is what? 2PQ, yes?
Yeah.
So it is simple. You are going somewhere else. 2 is there, yes? Multiplied.
Mhm.
What is the value of P?
The value of P.
0.993
No, that, yeah.
multiplied by what? 0.007. If you do, you will get the value, whatever the value will be there. This is the value of heterozygous individual in that population.
Mm-hmm.
You get it?
Yeah.
So just find out the value. No, I'm not getting you from here. Okay. What exactly
Well,
you are doing here?
so I'm using the second equation. So 1 is the total.
Uh-huh.
And this is Q squared.
No, that is what I'm saying. We don't have to use P square. Already we got from the P square, from the Q square, yes? We got Q,
Yeah.
correct? What was the Q
Yeah.
value? Q value is already, you got it here.
Yeah. But to find heterozygous.
You know, so heterozygous, to find out, you need to PQ, yes?
Mm-hmm.
P value is what? Here already you found the P value,
Yeah.
0.993. Q
Mm-hmm.
value is already here. So technically you are overcooking. You understand? So already
Okay.
numbers are there.
Okay.
You get my point? So can you
Yeah.
please give me the answer? Look, here, if we see this part, what will be the answer of this now? whatever the answer will come, it will be the individuals percentage probability of these individuals in that population.
Mhm.
Can you tell me now?
So it would be 0.013 or 14 when you round it up.
Yes, 0 point, let's say 0.014. Yes,
Yeah.
this is there. Yes.
Mhm.
Now, if I ask you a question, how many individuals are homozygous dominant? How you'll find out? Now you will be talking in numbers.
Yeah.
We already know 1 upon 20,000, they were homozygous recessive. Yes.
Mhm.
Now, can we use this data to figure out how many individuals will be? This is a question for you in future, not now. You understand? But
Is it
normally in
0?
exam, they will be asking you this question. They
Okay.
will give you number of homozygous recessive in one population, and they will be asking
Mhm.
you find out the frequency P or heterozygous like this, and you can easily
Okay.
find out. Yes, I'm
Yeah.
giving you one, question how you can use these values, this probability, yes, this probability to find out exactly how many out of 20,000 are heterozygous and how many out of 20,000 they are homozygous
Yeah.
dominant. Okay.
Okay.
I don't know by using 0.007, how can we get one? Can you crack one way now?
You square that,
Okay,
which was, I think.
do it.
We already know what Q squared was, so we can just
Exactly.
already
Now,
know what Q is. We can just square that. We already know what P is, so we can just square that value.
no, tell me how many individuals they will be homozygous dominant. How will find out this thing? I got it. I mean, this already we know, yes?
Yeah.
This already we know, but using this formula to get this number to get one, it will give us the idea how to get this, use this number to get what? The number for the others.
Okay.
Yeah.
So using 0.007, you would like square
Yeah,
that.
like, can we keep this thing for the next session?
Okay.
This will be a good thing. I'm doing this thing for the first time.
Okay.
Yeah, so we keep it for the next time. Okay, so we
Mhm.
stop here. Now this is called Hardey-Weinberg equilibrium. There
Mhm.
are certain conditions which are required for the Hardey-Weinberg equilibrium. Okay,
Okay.
there are conditions. These conditions, if they are there, only then Hardey-Weinberg equilibrium or equation is valid. Otherwise,
Mhm.
it is not valid. It cannot work. First condition,
Okay.
what should be? That there should be no genetic variation in the population, no genetic changes, no mutation.
Yeah.
Second thing, there should be what to say, there should be large number of population size should be very large. What is the
Mhm.
advantage of having population size very large?
Um, that there's more variation.
No. If the population size is more, chances
Yeah.
of variation become less.
Oh, okay.
Because if any variation happen, it will not be having that big impact. For example, if a population has only 20 individuals, okay, but
Mhm.
in those 20 individuals, if one individual change, the whole population dimension will change. But if
Yeah.
we have 20,000 individuals and out of those 20,000, one or two individuals they change, overall impact on the population will be minimal. No, very less.
Mhm.
And we learned Hardy-Weinberg equilibrium can work best if a population is stable, no genetic
Yeah.
variation.
Mhm.
Correct? Third
Yeah.
thing, third thing which should be there in that population, there should be random mating.
Yeah.
Okay, this is
Mhm.
very, very important. Okay, this is
Mhm.
really very important. It should be, because if it is non-random, what will happen? You are favoring one particular trait over the other. So
Mhm.
you are influencing, correct?
Yeah.
Okay, now if I ask you one question, peacock, the
Yeah.
males, they display their colors, yes, in front of the female.
Mhm.
It is part of random or non-random.
Pardon?
It is part of random mating or non-random mating.
Non-random?
Reason. Answer is correct.
Because a female would want to go to a male who has like better feathers.
Exactly. So a female is actually turning biased, because
Yeah.
the more attractive kind of colors means an individual is more healthy. It
Yeah.
has more power. So many things are associated. So you are influencing the other mates to get attracted towards you. So whenever anything is like this, it is non-random. Okay.
Okay.
Is it possible to happen in the normal life? Impossible. That is why Hardy-Weinberg theorem is actually, it is not in reality. It is just what we call it, theoretical.
Yeah.
Okay.
Mhm.
And the last thing that we must remember, the population, it should be isolated. What is the advantage of isolated population? The
There's no
Hardy-Weinberg theorem can apply only and only to isolated population. What does it mean?
it means populations that are not interacting with other species.
No, the point is no other gene from outside can enter, or no gene can leave, or allele can leave that population. They are confined into one area. So
Mhm.
immigration and or immigration, flow off, flow out of gene and flow in of the gene, it is not there. All the genes, they are present in one population. There is no inflow or outflow of the genes. So
Mhm.
genetic pool remains the same. You get my point?
Yeah.
And then there should be no, what we call selection pressure. There should not
Mhm.
be any selection pressure. I don't know whether you can, because this is new term for you, I have noticed. So there are 5 things which should be there. Only then the Hardy-Weinberg theorem is applicable. What is first thing? No genetic variation. Okay. There should
Yeah.
be random mating. Number 3, what will be? There will be large population size. Yes.
Mhm.
Number
Yeah.
4, it should be what?
I-
The population should be isolated. And number 5, the population should not be under selection pressure. This thing, the
Mhm.
selection pressure, bottlenecks, okay, and then founder effect. Inshallah ta'ala, we'll be doing these kind of terms in next session. Okay.
Okay.
So I'm done with the class today. I hope you got this Hardy-Weinberg.
Yeah.
Okay. So shall I
Mhm.
end now?
Yeah. Okay.
Okay. Take care. Take care.
Thank you.
Bye
Bye.
bye.